So what is the integral test? Well, we can use the integral test to help determine convergence of a series or divergence if the term that we are summing, if it is easy to integrate, right? So suppose we have the sequence a sub n, and they're all positive terms. We know that everything's positive. Well, what this says here is that we can let that term, the nth term, be a function of n, as long as f is continuous, positive, decreasing function of x. For all x that are bigger than some specified n, capital N, a positive integer. So the series, the sum of that, starting from that integer n to infinity, and the integral from that integer n to infinity of the function of x, as opposed to the term, the nth term, they're either going to both converge or both diverge. And so just to repeat, what we're doing when we use the integral test is we're letting the nth term be a function of n or x, starting at some value. We normally say from n equals 1, so our capital N would be 1 to infinity. And if the integral converges to a specific value, then the series would also converge to that value. Similarly for divergence. And so if we think about the example where we just showed that this series converged to 2 from our last video, and we consider, each of those terms to be represented by one of these blue shaded regions. Well, remember, we took that and we treated it like f of x equals 1 over x squared. And we said that that integral from 1 to infinity of that function converged to 2. And so what you see here, my curve, that is the function, and it is bounding completely above all of those sums. So if that function has a limit of 2 as we approach infinity, then the sequence, the series of all of those terms added up, is also going to converge to 2. So let's talk about the p-series. And we did an example in the last video that harmonic series 1 over n is a divergent p-series. So a p-series is when we take the sum from 1 to infinity of 1 over n raised to some p-value. Okay, this p-value here. And p can be any number. If p is greater than 1, it's going to converge. And if that p-value is less than or equal to 1, it will always diverge. So this is just a specific type of harmonic series. Okay? So what we're going to do here is we're going to show this. We're going to prove that this p-series, the sum from 1 to infinity of 1 over n to some p-value, converges if that p is greater than 1, and it diverges if p is less than or equal to 1. And in order for us to do this, we're going to look at 4 situations. Okay, we're going to say A, what happens when p is greater than 1? B, what happens when p is less than or equal to 0? C, what happens for a p-value that is between 0 and 1? And D, what happens when p is actually equal to 1? And so from what I told you above, the only way this p-series is going to converge is if p is greater than 1. So I'm going to show you it converges in that situation, and then to show you it diverges for every other situation, we'll do the other three examples or three parts of this problem. So the first thing we'll do is we'll say, okay, well, what happens if p is greater than 1? Well, then we have our function, because we said using the integral test, we're going to treat those terms like a function. So we have x to the p. And this is going to be positive. It's a decreasing function of x. Okay, so we have a positive decreasing function of x. All of the terms are positive, and they're constantly getting smaller. So since my integral from 1 to infinity of 1 over x to the p dx, well, this is equal then to the integral from 1 to infinity of x to the negative p dx. So we're faced with dealing with this improper integral. And when we deal with an improper integral, we replace that infinity with a b. So we're going to say this is going to be a limit as b approaches infinity, because we can't really do calculations with infinity of that integral x to the negative p dx. So integrating the limit as b goes to infinity, you add 1, so I've got negative p plus 1, and that goes into the denominator, over x to the negative p plus 1 from b to 1. P is just a value here. It's a constant, so I can pull that in front. I've got 1 over, I'm going to rearrange that, 1 minus p, times the limit as b goes to infinity, and I'm dealing with x to the negative p plus 1 from b to 1. So I pulled the denominator out in front. I have this numerical exponent here. So I'm going to plug my b and my 1 in. I've got 1 over 1 minus p. The limit as b goes to infinity of b to the negative p plus 1 minus 1 to the negative p plus 1. So that's all up in my exponent. Well, that second term, 1 to any power is just going to be equal to 1. So this is 1 over 1 minus p. I've got the limit as b goes to infinity of, now that's b to a negative exponent, so I can write that as 1 over b, and if I had factored out the negative, that's going to become p minus 1, and then I have minus 1 here. And so just to clarify, right there, we have negative p plus 1. If I wanted to say the whole thing is negative, that's negative p minus 1. And so because that was negative, I put it down into the denominator and made it positive. So if I look at evaluating this and plugging in infinity for my b, I've got 1 minus 1 over p. That would be 1 over infinity to the p minus 1 minus 1. 1 over infinity, we know, goes to 0, which gives me 1 over 1 minus p. I've got negative 1 in my parentheses, or just 1 over p minus 1. So this is a finite value, and because we get a finite value, we know that it converges. I do want to point out that this is not the actual sum. We don't know what p is, but we do know that it's finite. And because it is finite, we can say, all right, well, this converges. So it only converges when that p value is greater than 1. So let's look at those other cases to show that in all the other situations, it would be divergent. So if p is less than or equal to 0, so we have a negative p-value, we know it would be divergent by the nth term test. And remember, the nth term test says that if the nth term becomes increasingly large, then it's going to be divergent. And so what we mean by that here, the sum of n equals 1 to infinity of 1 over n to the p. So if I let that be equal to a negative value, negative p, then that would be the same as 1 over n to the negative p, which is n to the positive p. And what we can see here is as n becomes larger, then n to the p becomes larger, right? The bigger number I'm raising to a positive power, then the term is going to continually be bigger. So then we'll look at, well, what if p is fractional? And by fractional, I mean between 0 and 1. Well, I can come over here and say, well, that's the same as saying 1 minus p. If I subtract the p, then needs to be a positive number bigger than 0. And that integral then from 1 to infinity of 1 over x to the p dx, well, following a similar argument from what we just did in the first part, and I'm not going to work it all the way out, but we end up with 1 over 1 minus p, the limit as b goes to infinity of b to the 1 minus p minus 1. So, and I'll go back and let us see. So we were doing this similar improper integral on the last screen, and we ended up with something that was 1 over this, right? But that's not what we have here. We have some b value raised to a power, and eventually what we're going to be doing is putting b to some power take away 1, infinity to some power take away 1. This is just going to be equal to infinity. If it's equal to infinity, we know it's divergent. And if I skip back just one page, I'll just re-explain what I'm talking about here. We're looking at, we get something very, very similar for that improper integral, but it was in the denominator. So that went to 0. And in this case, it doesn't go into the denominator. We can show that it's infinity minus 1, which is infinity, which is, again, divergent. So our last situation for this problem would be to say, well, what happens if p equals 1? And if p equals 1, this sum, n equals 1 to infinity of 1 over n to the p, that's just the sum as n equals 1 to infinity of 1 over n, which would be 1 over 1 plus 1 over 2 plus 1 over 3. All right, and this is a harmonic series, and we said that the harmonic series is divergent. So the only time it would be convergent, it only converges if p is greater than 1. It only converges when p is greater than 1. If p is less than or equal to 1, and we showed 0, between 0 and 1, and then equal to 1. We ended up with, it went to infinity in every case, and those were all divergent.